the robotic field. It's a great pleasure to have Professor Majumdar from Bayesian with us today. He got his undergraduate degree from UPenn, PhD from MIT, the postdoc at Stanford. He has been interested since 2016. 17. He has won many awards, including the NSF Career Award and several Best Paper awards, including the most prestigious Best Paper Award from IJRR. And he's here today with us to share some of his work on safety and the guarantees for learning-based control of robots.
All right, yeah, thanks so much for coming. Thanks for the invitation. This is actually my first in-person external talk in, I guess, more than 2 years. So I'm really excited to be here. So our group at Princeton works on enabling agile robotic systems, things like unmanned aerial vehicles, to operate with guaranteed safety and performance in complex environments. And today what I'm going to tell you about is just, I guess, one piece of that work that we've been thinking about in the group that has to do with machine learning. So I guess as we've seen over the last decade or so, there's been a tremendous amount of excitement and adoption of machine learning components, deep learning in particular, in a multitude of different applications in robotics, manipulation, drones, and autonomous vehicles, and many other applications as well. And I think a lot of this excitement has been driven by the power of machine learning, deep learning in particular, to handle rich sensory inputs, things like vision or depth, and process that into representations that can then be used for downstream tasks such as control and planning. I think while this is tremendously exciting as a roboticist, in some ways this is also kind of scary. So one question that I'm going to think about, the main question today, is can we provide any kind of guarantees, any meaningful mathematical formal guarantees on safety and performance for these learning-enabled robotic systems, and specifically when we have neural network components as part of the perception and control architecture for these kinds of systems. So there's been some work kind of in this area over the last few years, mostly under the umbrella of safe learning. So typically the safe learning formulation is kind of as follows. So how can we ensure that your robot, as it is learning to perform, let's say, a new maneuver, doesn't violate any safety constraints during this learning process? So just to make things concrete, imagine that you're learning a new maneuver for a drone. The typical kind of safe learning formulation would be to try to ensure that as the robot learns, like as it updates policy, how do you make sure that it doesn't violate any of the safety constraints, or doesn't collide with the obstacle of the ground, for example. And there have been a number of different approaches to try to tackle this problem of safe learning. So for example, based on Hamilton, Jacobi reachability theory, robust MPC, Gaussian process regression, and also techniques based on formal methods. One thing I want to emphasize is that typically the safe learning formulation considers safety or tries to ensure safety during the training process. So as the robot is updating its policy, how do you make sure that it doesn't do something crazy and kind of crash into things? What I'm going to focus on is slightly complementary, somewhat different from this typical formulation. I won't focus on safety during the training process, but what I'm going to focus on is safety during the testing or deployment phase. So typically in the safe learning formulation, the environment that the robot is operating in is assumed to be fixed, and the thing that changes is the robot policy. Here I'm going to ask, what happens if you learn based on some data set of different environments? How can you say that you're going to generalize to new environments that were not part of your training data set? So just to make this concrete, this is a running example I've used throughout the talk. Imagine that you have a drone and you're training maybe some kind of obstacle avoidance or a navigation policy. Imagine that this is a neural net and you're kind of like training it end-to-end to process visual inputs or depth images into actions. And let's say you're doing this based on some finite data set. So these are different environments, 3D geometries from the Stanford indoor-outdoor data set. So let's say you just have a number of these 1,000, for example. You train your neural network to do the task you're interested in this case, obstacle avoidance or navigation. The question we're interested in is what happens when you deploy this learned policy in a new environment. So the 1,001st environment, something that was not part of your training data set, some environment that you'd never seen before. How can we guarantee kind of formally that your robot will succeed, maybe with some high probability in such a new environment? So I guess just to give you a sense for why this might be challenging and how production systems struggle with this. This is a Tesla autonomous car, or I guess a semi-autonomous car that's driving down a highway around kind of twilight time. The interesting thing is if you look at the perception system for the car, it's actually seeing the sun, which is kind of low down in the sky, and it's interpreting that as a yellow traffic light right here. And that's causing the car to hit the brakes because it sees a yellow traffic light. In this case, the human driver is paying attention, and if you look at the bottom of the video, the human driver takes over and kind of prevents the car from coming to a stop. But if this was truly autonomous, this could be pretty dangerous. So I see this as a kind of problem of generalization. So Tesla, I guess, has gigantic amounts of data that they've collected to train their perception systems on the giant neural network. But it has never encountered this specific scenario before, and it's failing to generalize to this situation. If you look at a different domain, so this is OpenAI's Rubik's Cube solving manipulation system. So I think really impressive in terms of demonstrations. But again, if you look at the success rate on kind of new initial conditions or new blocks, success rate as they were reported in the paper. So it ranges from around 20% to 60%, depending on the initial conditions and kind of the physical parameters of the block. So what I would argue is that current learning-based systems, particularly based on deep learning, fail to generalize even to mildly different environments than what they were trained on in the kind of training phase. And I see this challenge of generalization as really fundamental, as a fundamental technical challenge. If we want to deploy these learning-based systems out in the wild and kind of make some guarantees on how they will behave. Recently, there have been quite a few empirically focused efforts, particularly in the reinforcement learning community, trying to improve generalization. So techniques based on domain randomization, data augmentation, regularization, bisimulation, and others. The focus of this talk will be slightly different. So of course, we do care about empirical generalization, just how well does the system do. But mostly I'll be focusing on this question of can we provide formal guarantees, mathematical guarantees on generalization to new environments. So today in the talk, I'm going to focus on settings that I think are like particularly appealing for using deep learning, but also challenging for making guarantees on. So these are systems that have robotic systems that have potentially nonlinear or hybrid dynamics, rich sensory inputs like vision or depth, and also neural network-based control policies. And my goal today is basically to convince you that it's possible to make some meaningful guarantees on generalization for these kinds of different settings. And I think traditionally this has been a pretty challenging problem to make guarantees. And my goal is basically to convince you that it's possible to make some at least kind of reasonably meaningful guarantees. All right, so here's the formal question.
I didn't want to ask a question.
Yes.
From the beginning. So when you say generalization, something generalization is similar to what we encountered in regression or classification, or semantic generalization where you learn new concepts or new things about the environment.
Yeah, excellent. So I'm actually going to clarify that just in the slide. So I'll give a formal problem statement. So it's more kind of the former rather than the latter, but hopefully it'll be clear. But I guess it's not just asking again. So yeah, here's the formal statement. So your robot has some dynamics. X is the state. Use the control input, and E is the environment that the robot is going to be operating in. So I'm using the word environment pretty broadly here to refer to factors that are external to the robot. So if you're thinking about obstacle avoidance or navigation, think about the kind of geometry of obstacles around the robot. If you're thinking about manipulation, think about the object that the robot is trying to manipulate as corresponding to the environment. The main assumption I'm going to make, at least for the kind of beginning of the talk, is that there's some true but unknown distribution D from which your environments are drawn. So this could be an extremely complicated distribution, like the distribution of all objects, for instance, that your robot might encounter. I'm just going to assume that there is some distribution. We cannot necessarily write it down. We don't even know the space necessarily on which this distribution is defined. But the main assumption to begin with will be that we have some finite data set, so I'll call that data set S, of different environments, so like obstacle environments or objects that are drawn from this underlying but unknown distribution. The robot has some sensor. So again, we're specifically interested in kind of high-dimensional sensory inputs like vision or depth. And the goal is to learn some policies, some control policy that maps sensor measurements or histories of sensor measurements to control inputs in order to minimize some cost. So I'm using this notation here, C by E. This is the cost of deploying some control policy phi on environment E over, let's say, some finite or potentially infinite time horizon. And I'm going to assume that the cost is bounded. So the cost of deploying any policy on any environment is bounded between 0 and 1. Just to be concrete, I guess if you're thinking about obstacle avoidance, you could say I'll assign a cost of 1. If my robot collides with something, I'll assign a cost of 0 if it gets to the goal, and maybe something in between if it gets close. Yeah.
The E in the last line without a subscript means all of them in S or just one?
In the cost.
Optimize the cost of optimize over one environment over all.
Okay. So I haven't clarified that yet. So this is just defining the cost of one policy on one environment.
Okay.
On the next slide, I'll answer the specific question of exactly what we're trying to optimize. The last assumption, though, is that for any policy, we can basically evaluate the cost. So we can run our policy on the training environment and just see how well it does. And we're going to use that for optimization. So yeah, I guess hopefully this answers that question. So what we're trying to do, the ultimate kind of problem formulation here, is to find some policy, maybe think of this as a neural network, that minimizes the expected cost across future environments that are drawn from this unknown but underlying distribution D. So it's not one specific environment, it's not even the training data set of environments, it's in expectation over environments that are drawn from this underlying distribution. In some cases, I guess for some kind of mathematical reasons that I'll go into later, it's going to be helpful to find not just a single kind of deterministic policy, but rather a distribution over policies. So in this formulation, this is slightly more general than the previous slide. We're trying to find some distribution over policies denoted by capital P in order to, again, minimize the expected cost.
And would safety constraints be built into the cost?
Yes, yeah, so that's what I'm assuming. So you can, let's say, like assign a cost of 1 if you violate safety constraints and 0 otherwise. But yes, that is definitely good. So in this formulation, there are 2 expectations. So there's the inner expectation, because we're randomly kind of choosing a policy from this distribution P that we're going to learn. The outer expectation, I think, is the real kind of main technical challenge here. This distribution, again, is unknown to us. We don't have explicit access to it. We only have indirect access to it in the form of a finite training data set of input. Okay, so the main kind of technical hammer that we're going to use in this talk that we've been exploring in my group comes from what's known as generalization theory in statistical learning theory. This has primarily been developed in the context of supervised learning, so things like image recognition. The main kind of technical meat here is going to be to extend and translate some of these techniques from generalization theory from supervised learning to this like policy learning or control setting that we are interested in. And basically what this will allow us to do, what this theory will allow us to do, is come up with upper bounds on the quantity that we're interested in. So upper bounding the expected cost across future environments that your robot will encounter. And then the algorithmic approach is to basically find policies or distributions over policies that give you the best possible guarantee. So try to minimize this upper bound. We can do this in certain settings via convex optimization, geometric programming in particular. In kind of other more generic settings, we're going to be able to do this using stochastic gradient descent or derivative-free optimization. So that's the kind of basic overview. Before I go into the details a bit more on generalization theory, I just want to make a kind of philosophical point, which is what do I really mean by guarantees in this talk? So anytime I use the word guarantee here, what I mean is a guarantee in the frequentist sense. So I want to be able to say that if I take my control policy, if I deploy my robot in 1 million different environments, then it's not going to crash, let's say, in 99% of them. So that's the kind of meaning I have in mind here. This is somewhat different from the kinds of probabilities you might compute using a Bayesian approach, for example, based on Gaussian process regression. What I would argue here is that when we're talking about making guarantees, particularly in safety critical robotic systems, we want frequentist style guarantees rather than Bayesian style guarantees. We want to be able to say that if I deploy my drone in millions of environments, then it's going to perform well, not collide with things in some proportion of them. This is not something that a Bayesian style reasoning necessarily gives you, because Bayesian probabilities are kind of inherently tied to the prior and how meaningful the prior is. So if you're a Gaussian process, that gives you like a 95% confidence. This doesn't necessarily mean that if you deploy your robot in 100 environments, 95% of the time you're going to remain safe or perform well. At the same time, though, Bayesian style reasoning is extremely powerful in terms of allowing us to incorporate priors, so prior knowledge or inductive biases that we might have either on our kind of robotic system or environments. And so I think one kind of question is, how can we provide guarantees that are frequentist in nature while still being able to incorporate this prior knowledge or inductive bias that we might have on our problem or system. And ideally, if you have better inductive bias, if you know more about your environments kind of a priori, then this should lead to stronger frequentist style guarantees. This is where PAC-Bayes theory comes in. So PAC stands for probably approximately correct Bayes theory. And I'm going to, I guess, argue that PAC-Bayes gives you the best of both worlds in some sense. It allows you to incorporate priors while ultimately still giving you frequentist style guarantees. These bounds originally were developed roughly 20 years ago, primarily in the context of supervised learning. And they provide some of the tightest known generalization bounds for classical supervised learning approaches, things like support vector machines. And over the last 3 or 4 years, there's been a resurgence of interest in PAC-Bayes for explaining and also promoting generalization for deep neural networks, again, specifically in the context of supervised learning, things like image recognition tasks. So what I'm going to do is give you a really quick, just a kind of 5-minute crash course on PAC-Bayes. So if you haven't seen PAC-Bayes before, I want to give you the main result in the stuff. So I'll first describe it in the context of supervised learning, and then talk about how we can extend it to the settings that we're interested in here. So in the supervised learning setting, we have some input space and some label space. So think about the input space as maybe the space of all images, if you're thinking about object recognition, and the label space as different object categories. Again, we're going to assume that there's some true but unknown distribution over your inputs, some true distribution over images that your system might encounter. And you're working with some hypothesis space. For concreteness, you can think about neural networks with a certain architecture that is parameterized by weights W. And you have some loss function that tells you how well any particular hypothesis does on a particular image. And again, I'm going to assume that the losses are bounded between 0 and 1. So PAC-Bayes theory applies to supervised learning algorithms that have the following kind of general structure. Again, we're going to be working with not specific hypotheses, but rather distributions over hypotheses. So I'll let this kind of calligraphic P denote the space of probability distributions on your hypothesis space. Again, if you're thinking about neural networks, think about distributions on the weights of the neural network. So PAC-Bayes basically assumes that you have some prior distribution P0 that you fix before observing any data. So this is what allows you to incorporate prior knowledge, inductive biases. I'll say more about how to choose this prior, but for now, just assume that you have some prior. You then observe some data set, some finite number of examples of images and labels, and then you choose some posterior distribution, capital P, based on this set of examples that we saw, and potentially also based on your prior. So PAC-Bayes basically then allows you to relate the training loss, which is the loss of this distribution P that we're trying to learn given the data set. So this is the expected loss on your finite number of examples. So it relates that to the true expected loss, which is the quantity you really care about. So this is the expected loss on future data that you haven't seen yet, that's drawn from this unknown but underlying distribution over inputs. this is the main kind of result from PAC-Bayes. So it says that with probability 1 minus delta, so delta is a parameter that you get to choose. It's kind of like a confidence parameter. With probability 1 minus delta or the sampling of your training data set, the following kind of bound holds. So we can upper bound the true expected loss, which is the quantity where we kind of care about the generalization performance in terms of two quantities. So the first one is your training loss. So how well does this distribution that you're trying to learn perform on the training data set? The second term you can think of as kind of a regularization term. This is a complexity term. So the KL divergence is the KL divergence between your posterior distribution, which is what you're trying to synthesize or learn, and the prior distribution. And basically, one way to think about this is saying, try to find some distribution over hypothesis capital P that fits your data well, minimizes the training loss, but at the same time doesn't deviate too far away from your prior distribution. So you can think of this as kind of preventing overfitting. And this holds for all posterior distributions capital. So maybe let me actually pause for a second and see if there are questions on this result. Yes, sorry. So capital N is the number of training examples that you had access to. Was there Jesse another hand or?
No, I just was recognizing this from half hour ago. Jinda and I were talking about a paper that had something in there that they were calling regularizer.
Okay.
We were discussing what the heck is this regularizer, and you just explained.
Okay. All right. Good. Yeah. Yeah. So this is a specific kind of regularizer that the PAC-Bayes is specifying for us. Okay. So
There is one other question.
yes. Go ahead. Sorry.
So what if we go back to the comment about T0, the initial trial not being really close to what actually.
Yes. Okay. Yeah. Really good question. So if your prior is like incorrect or bad, like doesn't capture reality, this bound will always be valid in a frequentist sense. So the bound could be bad, but the bound will kind of always be true at least.
Okay.
So you can then evaluate, like you can compute this bound and you can say, do I like this bound? Maybe not. Maybe then I need to do some work, collect some more data. But the bound will always be valid in a frequentist sense. And I think this is something that's different. Like if you've seen like Gaussian process regression, for instance, you don't get that kind of like frequentist guarantee. So if your prior is incorrect, you'll still get some number, but that number may not kind of correspond to like any like frequentist style guarantee. Yeah. So the prior is important, and I'll talk about how one might go about choosing the prior. But at least even if the prior is bad, the bound needs to be valid or correct. Yeah.
And this thing, I can choose P0 in favor of the result.
Okay. No. So you're not allowed to do that. So if I go back to the previous slide, so the prior has to be chosen before you observe any data, and then you fix it. Otherwise, you can go and say, okay, I'm just gonna choose some posterior, and then I'll say, actually, my prior was the same as the posterior, right? Yeah, something in the proof like breaks down, and there's a specific line that breaks, so you're not allowed to do that. Yeah, good question. Okay, so that's kind of in the supervised learning setting. So what I'm gonna just briefly outline is how we can take this theory from supervised learning and kind of extend it to the policy learning setting that we're interested in robotics. So again, in the supervised learning setting, you have some input corresponding to an image, some hypothesis that takes the input, maps it to a label, some loss function that tells you how well you did, and then PAC-Bayes gives you this guarantee upper bound on the expected loss on future input data. What we're going to do is take our policy learning setting that I tried to formalize a few slides ago, and basically map it onto this supervised learning formulation. So you can think of this as kind of a reduction. So we're going to think of the environment that the robot is operating in, the variable E, as corresponding to the input. The policy then corresponds to the hypothesis. So the policy kind of takes the environment and indirectly maps it to actions. Indirectly, of course, through sensor measurements. So the robot is not explicitly kind of seeing all aspects of the environment, but is only receiving sensor observations. But yeah, through those sensor observations, that determines some sequence of actions that the robot takes in any particular environment. And our cost function then takes this sequence of actions that results from applying the policy and tells you some cost, again, potentially incorporating safety constraints. And basically with this mapping, like if you think about the environment as the input, the policy is the hypothesis, the cost is the loss. You can make this more formal. I won't go into the details, but PAC-Bayes then gives you a guarantee on the expected cost on new environments. So this is kind of what that looks like. It's pretty much exactly analogous to the supervised learning setting. So again, we can define our training cost that we can evaluate given the training environments. The true expected cost is what we really care about, what we're trying to minimize. And PAC-Bayes says that with probability 1 minus delta or the sampling of the training environments, you can upper bound the true expected cost as a combination of the training cost and this exact same kind of regularization. So the algorithmic approach then is to try to find some distribution capital P. So you're allowed to take P to be whatever you want. So you want to find some distribution capital P that basically gives us the best possible bound, the best possible guarantee on generalization to new environments. So if we work with finite policy spaces, if you're trying to find a distribution over finite policy spaces, then it turns out that you can optimize this PAC-Bayes bound. You can find this distribution using convex optimization, geometric programming in particular. Of course, in general, we're typically want to be working with continuously parameterized policy spaces, things like neural networks. In that case, what we do is parameterize distributions over the weights of the neural network. So that's what defines a distribution P on your policy space. We then basically minimize this bound using stochastic gradient descent or derivative-free optimization. So at the end of that process, what we get are two things. One is a distribution over policies that you get from trying to minimize this bound. The second is the bound itself, which you can kind of think of as a certificate or a guarantee on generalization to new environments under the assumptions that we made so far. All right, so I guess how well does this do? So I've described a bunch of theories. So the natural question is, are these bounds tight? Are they meaningful, and so on? One of the first examples we tried this out on is a kind of quadrotor navigation system. And the goal here was mostly to convince ourselves that we can get some relatively meaningful guarantees for when we're learning neural network-based control policies. So the sensing here is a RGBD sensor. So you can imagine that a RGBD sensor is mounted on the drone. And this entire system, sensing and dynamics, are simulated here using the PAC-Bayes simulator. Here we're using a receding horizon control strategy based on motion primitives. So we have these pre-computed library of primitives, things like fly straight, turn left, back right, and so on. And basically what the neural network does here is takes in an input RGBD image and selects a motion primitive to apply. And then you do this in a receding horizon fashion. So you execute this maneuver or part of the maneuver and then replan using the neural network. So that's kind of the general architecture. And this is roughly what the kind of policies look like for different environments. So these are environments that were not part of the training data set. So we train a distribution over policies using PAC-Bayes theory, minimizing the PAC-Bayes bound. And these are kind of just representative trials on new environments. Here are the numerical results. So the top row is showing the number of environments. These are kind of the cylindrical obstacle environments in the video. So the number of environments we use for doing this training with PAC-Bayes. And this is the bound on the success rate. So success just means going to the end of the kind of track without colliding with obstacles. You can think of this as 1 minus the cost, if you like. So the bound that we get from PAC-Bayes ranges from around 75% to getting close to 80%, 79% or so. And if we estimate the true expected cost on new environments, just via exhaustive sampling of environments, so we see that it's around 82% or so. So we get relatively tight bounds in terms of the success rate using PAC-Bayes. So I think this was like fairly exciting for us. I think traditionally it's been challenging to come up with these kind of generalization guarantees when you have neural networks. And with this machinery of PAC-Bayes, we can get bounds that are at least kind of reasonably meaningful in this setting. We also implemented this on a hardware platform. This is the Parrot swing drone, which is kind of a fun platform, which is a hybrid between a fixed wing and a quadrotor. So it takes off vertically and kind of transitions to a forward flight, as you see in the next slide. And these are the environments, or this is one specific environment. We have these cylindrical obstacles in our lab space at Princeton. And we're using depth images again. In this case, we are actually simulating a depth sensor. So the drone itself is too light to put a RGBD sensor on it. We have a Vicon motion capture system that's basically tracking the position and orientation of the drone and the position of the obstacles and sort of simulating what the depth image would look like from the perspective of the drone. So the only information that the drone's policy is using is the depth image. We're just using the Vicon system to kind of pretend that we have a depth sensor. And again, similar to the, sorry, yes.
What are the lines for calibration for the visual system?
So those were actually something for something else altogether. We didn't take them off, unfortunately, in this video. Yeah, I think we had a different team doing like optical flow, and there wasn't enough texture. Yeah. Go ahead.
Did you incorporate any noise to simulate that?
Yes, so in this example, we did not. I'll show a different example where we had a real RGBD sensor, and for that we did. Yeah. But this is just the kind of high dimensionality of the inputs that we were processing with a neural net, and this was trained in simulation and deployed on the hardware. We did a couple of other things for like simple Fourier transfer, which I'm happy to go into, but at least for this example, we didn't add noise to the depth. So in this example, the guarantee that we were getting from PAC-Bayes is approximately 93%, again, on the success rate. And the empirical success rate, if you run the robot in many different environments, we ran it in 30 different environments on the hardware. This was a 28 out of 30 successes, which is slightly higher than the PAC-Bayes guarantee. So the theoretical bounds kind of translate into the real hardware system, and I'll show some videos in a second.
And so way back, you said something about the environments being high IQ.
Yes.
And how did you kind of enforce that in the experiment?
Yeah, so we have some, I guess for testing purposes, we have some distribution over environments that kind of we just wrote down. We don't assume access to it kind of directly, but we have to specify some distribution. So in this case, we were specifying some support for the kind of probability distribution over obstacle location and some distribution over the number of obstacles in each environment. And then we draw samples from that distribution for training and testing. Yeah. Okay, so here's a video of the drone. Let's see. And these are again test environments, not environments that you do specific environments. Failures, I guess this is important to show. Right. So I guess one question I haven't addressed yet, and something that you asked is how to specify the prior that we're assuming that we have kind of access to or we can specify. And again, as I mentioned, I think that the prior provides a nice opportunity to embed some domain knowledge that you have on your environment or on your system. For the previous examples, we did a couple of things to embed some prior knowledge. One was just the choice of the motion primitive. You can think of that as kind of domain knowledge that you have. We also had a simple kind of base policy that scores different motion primitives based on the depth along those motion primitives. And then we were learning a residual on top of that using PAC-Bayes. Another approach that we've explored is to learn the prior itself. And there's a couple of ways of doing that. One approach is to learn the prior using some expert demonstrations, so specifically using imitation learning. So this is what we did with this manipulation example. So here the sensing is actually a real RGBD camera. We collected demonstrations of like grasping different objects using a 3D mouse. So these are demonstrations from a human. We use that to train a prior, and then we have an additional data set of environments, specifically from the ShapeNet data set that we use to train the posterior, again, minimizing the PAC-Bayes bound. We train this in simulation, and here it's important to add some kind of realistic sensing noise to the RGB images, which is what we did, and then we deployed that on the physical hardware system on new mugs, in this case, that were not seen during the training, as part of the training use. Again, in this case, the bound is approximately 93% from PAC-Bayes. The prior, so if you just rely on imitation learning, you get an 83% success rate. If you then fine-tune that using PAC-Bayes, the posterior success rate, kind of estimated, again, just using lots of different mugs, is 98%. And on the hardware system, these are 3 different random seeds, and we get a success rate of 100% to around 96%, depending on the random seed. Okay, so far in the talk, I've made this kind of important assumption, which is that your training and test environments are drawn from the same underlying distribution. Often this is not the case specifically for robotics applications. So the question I want to consider is what happens when your test environments are drawn from a different distribution than the training environment. The first question I'm going to talk about is, can we even detect when this happens? So can the robot automatically detect that it's operating in some environments that are drawn from a different distribution than what it was trained on? So this is the kind of problem of out of distribution detection over the detection. In principle, this could then allow the robot to act more conservatively if it detects that it's operating in kind of unfamiliar environments or sees its operations altogether and maybe asks for help from a human or something along those lines. The second question is, can we not just detect, but can we really learn policies that are robust to at least some distribution? Let me talk about the first question first. How can we perform out of distribution detection? Again, I'll use this kind of drone example as a running example here. So imagine that you have some distribution of environments that you train your system on, but then you deploy it in environments that are different. Maybe you have some wind that you didn't have during the training phase. Maybe you have more cluttered environments as well. So what we're going to do here is just detect when this kind of distribution shift happens, detect that the robot is operating in OOD environments. So I think there are 2 kind of important criteria that we would like an OOD detection scheme in these robotics applications to satisfy. The first is we would like to have some guaranteed confidence balance. So specifically, we want to have some bounds on the false positive and false negative rates of detection. So the robot detects that it's operating out of distribution, like what is the confidence that it really is, or what is the probability that it is kind of detecting that correctly. The second criteria, which is maybe slightly more subtle, is that we want to be sensitive only to task relevant shifts in the distribution. So maybe if there's some kind of little portion of the environment that changes, but that doesn't have any impact on the robot's performance, and sometimes we don't really care. Like we only care when there is a shift in the distribution that actually kind of negatively impacts the performance of the robot. So we have an approach that we've been developing that builds on this kind of PAC-Bayes methodology that tries to satisfy both of those criteria. The basic idea is that we train some policy using essentially the exact same method that I just presented using PAC-Bayes. That will give us a bound on the expected cost, the expected performance on the training distribution. We basically see if that bound is violated at test time. So if you deploy a robot and you find that the robot is doing worse than the bound said, then this gives you high confidence that the robot is operating out of distribution with some guaranteed kind of confidence level that you can get. So let me talk about the approach in some more slightly more detail. So the training phase, again, is pretty much identical to what I presented in the first part of the talk. So we train some policy, in this case, a single policy, not a distribution, using some more recent PAC-Bayes bounds known as de-randomized PAC-Bayes bounds. But it's the same basic idea. We find a policy that gives us a bound on the expected cost on future environments, future training environments. And then the cost here for the drone example is the minimum distance, or related to the minimum distance to the obstacles. So as the minimum distance goes smaller, the cost goes higher in this case. And same as before, we're learning some neural network policy that maps sensor observations in the form of depth images to actions, which are in the form of motion primitives that the drone can fly. So that's the training phase. So when you deploy your robot, I'm going to assume that you deploy it in some small number. So let's say K test environments. And the basic idea is to see if your bound on the cost that you get from PAC-Bayes is being violated on these test environments. So basically, you see that the cost on the test environments is larger than the guarantee you had for PAC-Bayes on the training distribution. And then this gives you high confidence that the robot is operating out of distribution. You can also use some concentration inequalities to actually get a bound on the false positive rate. So false positive means that the robot thinks it's operating out of distribution, but in fact it is not. You can also get some bounds on the false negative rate. So the robot says, I'm not operating out of distribution, but in fact the robot is operating out of distribution. The other kind of feature I want to point out is that the detection scheme here is sensitive only to task relevance shifts. So since we're looking at the cost, which is kind of a direct measure of the performance, if the cost is not impacted by a change in the distribution, then this out of distribution detector will not trigger, which is kind of what we want over here. So here's an example. This was the running example I was using with the drone. So during the training phase, there was no wind. And then in the testing phase, we're introducing a wind. There's a fan at the bottom left of the picture here. And we're slowly increasing the amount of wind that's being applied. And you see in the next step that as the amount of wind is increased, the drone gets closer and closer to this obstacle over here. And that's the signal basically that it's using to perform this out of distribution. So here's the kind of plot of the results. So the x-axis is showing the percentage of the wind gust. So 0 to 100% here is about 5 meters per second. And the drone is pretty light, so 5 meters per second has some kind of meaningful impact on the drone's dynamics. And as we can see, as the wind is increased, the confidence that the robot has that it is operating out of distribution keeps increasing, and you can potentially threshold. So you can say that if I'm 95% confident, then I know that I should maybe change my behavior and like stop operating in these environments.
Is it the control policy that is the process, or the knowledge about the environment?
Yeah, so in the training phase, the control policy is what's learned. And then we get this bound from PAC-Bayes on the expected cost on the training environments. And then during the testing phase, we're just fixing the policy and we're seeing if the bound is violated, basically. Thanks. Good. All right, so this approach that I kind of just outlined relies on failing essentially or getting close to failure in order to perform out of distribution detection. Another related problem is failure prediction. So ideally, we want to be predicting that your robot might fail before it actually fails, and then we come to a stop. So the failure prediction problem here is given some policy. Maybe someone comes to you with a neural network policy, some kind of black box policy. The goal here in this formulation, the failure prediction formulation, is to train some neural network that takes the sensor inputs from the drone and predicts if continuing to deploy the policy will lead to a failure in the future, given some set of training environments. And if you predict a failure, then you can kind of abort the maneuver, maybe execute some emergency maneuver that tries to prevent that failure from happening. And again, we can use PAC-Bayes theory. I won't go into the details, but we can basically use PAC-Bayes to train a failure predictor, in this case, given some fixed policy that gives us a bound on the false positive and false negative rates of failure prediction. Currently, I guess as a caveat, we can only do this within distributions. If we have some training environments, we can only do this failure prediction in new environments that are drawn from the same distribution. Currently, we're collaborating with some folks from NVIDIA to try to extend this to the out of distribution setting as well. So doing failure prediction in OOD environments. Here's a video that demonstrates, again, using this drone example. So this is an example where the failure predictor triggers because of an obstacle that's kind of occluded in the view initially, but then becomes visible later. And this is without the failure predictor. So we've crashed this drone a whole bunch of times. And these, in the next step, you'll see multiple kind of different environments. So true positive is when the failure predictor triggers and you would have crashed. So I guess to figure out whether or not we would have crashed, we are actually crashing the drone. False positive is when the failure predictor triggers, but in fact you would not have crashed. So if you continued, you would have just kind of narrowly missed the obstacles. True negative, failure predictor doesn't trigger, you don't crash. Let me pause the video here. So in these examples, the true expected failure rate of the policy that we're assuming is kind of handed to us is around 25%. The bound that we get for our failure predictor, the bound on the false positive plus the false negative rate, is around 13%. You can break up the kind of bounds individually if you like as well. On the hardware system, the true false positive plus false negative rate was around 6.7%, so that's below the bound, which is good. And on the hardware, there were no false negatives. So actually, false negatives, I guess, are what we really care about. So false negative is when you don't predict failure, but you do in fact fail. So we don't want that to happen. We actually have a way of trading off the rate of false positive versus false negative rates. So again, in these kinds of applications, you want your false negative rate to be low. Maybe you can be slightly more tolerant to a higher false positive rate for failure prediction. All right, so that's kind of the first question. So can we do out of distribution detection and failure prediction? I just want to briefly talk about some work we've been doing on learning policies that are robust to different distribution shifts. So we have this approach that we call dragging. The basic idea is to do distributionally robust optimization using the Wasserstein distance. So the formulation here is you have some training distribution and you have some Wasserstein distance or Wasserstein ball rather around the training distribution that you want to be robust to. The nice thing about the Wasserstein distance in particular is that it allows you to basically specify an underlying metric on the space of environments, which in this case we're kind of learning in wanted to capture features of environments that are relevant to the task. So in principle, you could have, I guess maybe one question is how do we even capture, like, what is a good family of distributions, a good set of distributions that you want to be robust to? What we want is to be robust to features in the environments that are actually relevant to the task, so not things like maybe color or other irrelevant features, but like geometry of physical shapes and so on. So we're learning this kind of latent embedding model such that distance in this embedding space corresponds to cost, so corresponds to performance, and that's the kind of metric we use to define our was-assigned distance. We then perform distributionally robust optimizations. We try to find a policy that gives us the best possible worst case guarantee, worst case over this ball of was-assigned ball of distributions. And we can do this using adversarial generation of environments. So we start from some training data set, we train a policy, we generate some adversarial environments that perform this distribution robust optimization. We keep iterating. I won't go into the details, but I guess I'll just point you to a video here. So we compared this approach, the policies that we get from this approach, to other techniques such as domain randomization. That's pretty common for sim to real transfer. And we found fairly significant benefits in terms of generalization, particularly from sim to real, if we use this approach for manipulation, for graphing in particular. Okay, so I guess I have around maybe 7-8 minutes or so. So I want to end with some directions for future and current work. One challenge with the method that I presented is scaling up the kind of strength of the guarantees. So the strongest guarantees here we were able to get were around kind of 93% or so. In practice, we want to be making even stronger guarantees than that if we want to like deploy these neural network systems kind of out in the wild. I think one option or one possible direction is just to scale up the size of the training data sets. We were using relatively small training data sets, at least by kind of industry standards. So we have some collaborations with some industry people to really try to scale this framework up using larger data sets. Another, I think, potentially really promising direction here is to move beyond end-to-end learning, which is what we were doing here, and to have some guarantees that are more modular in nature. So typically in practice, like people have some state estimation loop that takes raw inputs, sensor measurements, images, and converts them into state estimates. And then you have a separate kind of planning or control module that is more traditional using like sampling-based planners, for instance. So one question here is, can we combine some of these techniques from PAC-Bayes, basically give us a bound on the state estimation part, the bound that takes images or depth images and translates them into state estimates, and then somehow combine that with a planner in order to make guarantees on the whole kind of end-to-end performance of the system. I think another promising set of directions is to find other ways of embedding prior knowledge. So this can really help improve the strength of the generalization guarantees and also the performance. So we've explored a few different ways. So one is using generative models. So the idea here is maybe you don't know exactly what the distribution of environments is going to be, but you have some kind of approximate like distribution, which you can then use to specify a prior, which you then fine tune using some smaller set of real world environments. We've also been thinking about how to combine these techniques with kind of techniques from control theory, so robust control and reachability analysis, which can make your controllers more robust to lower level kind of disturbances like wind gusts and so on. And finally, we've been thinking about generalization bounds in the meta learning context as well. And we had a paper at New York last year. So just to conclude, so I presented this machinery specifically using PAC-Bayes that allows us to provide guarantees on generalization for systems that have rich sensory inputs like region or depth and neural network-based control policies. I presented some of our work on doing auto-distribution detection and auto-distribution generalization. So yeah, I guess hopefully I convinced you that there's some kind of potential here to use these theoretical techniques to make guarantees on generalization and safety for learning-based control of robots. So if you're interested, we have a few papers that I'll just point you to. So our earlier kind of work on PAC-Bayes was published at Coral, so Conference on Robot Learning and IDRR, and the OOD detection work and OOD generalization work was presented at Coral and also RAL, and the meta learning work was presented at Europe. So this is our group. So we have currently 7 PhD students. We actually had one postdoc who recently finished up, joined the autonomous vehicles team at NVIDIA. This is Marco Pavonin's group. So we're currently looking for a postdoc. So if you're interested or if you know anyone who's interested, definitely feel free to get in touch. All right, so I'll leave you with this introduction slide and take any further questions you have.